at the end of the previous lecture, and today I'm going to continue this discussion. Hydrodynamics is a very old subject. If you want to learn it, one of the good place is the volume 6 in the textbook by Landau and Lifshitz. Usually people don't go that far in the course. People usually go like volume 1, 2, 3, and then jump to Peskin and Schroeder, and then probably Polchinski. So I'm going to tell you what you need to know about hydrodynamics in a slightly more modern language than what is usually done in the textbook. So I alluded to in the previous lecture that the hydrodynamics is some kind of effective field theory for degrees of freedom that are long distance in the plasma. So it's convenient to draw a picture of a fluid just for visualization. We have some particles that move around, and then some particles move. If you follow the trajectory of one, they scatter. There is a typical length scale, the mean free path. And we are looking at the distance scale much bigger than the mean free path. Usually, that means that in terms of energy, in terms of frequency and momentum, the frequency and momentum has to be much smaller than the inverse of this mean free path. Typically, this one is always less, or at least of the same order of magnitude as the temperature. So here we are discussing the regime where all the momentum and energy scales are much less than the temperature, at least. For weakly coupled theory, actually the mean free path is much bigger than the inverse temperature, so this omega and Q is restricted to be much smaller than T. For strongly coupled theory, like N equal 4 super Young-Mills at large top coupling, as we will discuss, the condition for the applicability of hydrodynamics is omega and T much less than the temperature. So one consequence of that is that if you look at the Bose-Einstein formula that everybody knows, the occupation number of a mode is e to minus is 1 over omega divided by T minus 1. When omega is much less than T, the occupation number is much bigger than 1. Okay? So that means that hydrodynamics is a classical theory, because we are describing modes that have occupation number much bigger than 1. Usually hydrodynamics at finite temperature is not a quantum theory. Okay, so that is the regime of validity of hydrodynamics. Now we are going to formulate the hydrodynamic theory for the simplest case. In the previous lecture, we mentioned that the hydrodynamic degrees of freedom may contain, for example, Goldstone bosons or the unbroken U1 gauge field. But in this case, we will restrict to a simplest kind of fluid, a fluid where the only degrees of freedoms are the conserved energy density, conserved energy, and momentum are conserved. And we assume that there are no other conserved charges, or if there are in the theory, they are the plasma is overall neutral with respect to that conserved charge. For example, if you talk about the electroweak plasma, we will assume that the lepton number and baryon number is all 0. So in this case, we have d mu T mu nu equals 0. So before proceeding, let me explain why I put quote in this effective field theory. Usually when we formulate an effective field theory, we have a Lagrangian formulation, and then we can make a derivative expansion. When we, in principle, with a sufficient number of counter terms, we can compute everything. We can compute or parameterize all correlation functions. In the case of hydrodynamics, unfortunately, the system we are considering is dissipative. So there is no good Lagrangian formulation that I know. Perhaps maybe gravity will tell us what is the correct Lagrangian formulation of hydrodynamics. But here I am proceeding in the standard way, using the formulation in terms of the equation of motions instead of in terms of action principle. So I'm writing down here the equation of motion for hydrodynamics. The mu T mu nu is equal 0. If you look at this equation, it doesn't close because the number of components of T mu nu is 10 in 3 + 1 dimension, and the number of equation is 4. So we need additional conditions to close the equations. And that comes from a very important assumption, that is the assumption of local thermal equilibrium. Thermal equilibrium allows us to reduce a very large number of microscopic characteristics of the system to a small number of macroscopic quantities. We know that in thermal equilibrium, the system can be described in terms of, say, the temperature and the chemical potential. Here, we assume there is no conserved charge, so the only thermodynamic variables characterizing the system at rest is temperature. But now we assume that the system has some spatial variation. So T can be a function of X. And in hydrodynamics, the whole elementary volume of fluid can move with some velocity. So we also have the local velocity, u mu, that is the velocity of volume of a fluid located at the position X, and at the velocity at time t. And u square has to be equal -1. This is the unit vector, unit time-like vector. So if we can express T mu nu in terms of these 4 variables, so one is the temperature in the rest frame, and the other are the 3 velocities, then we will close the system, this system of equations. Okay. So, any questions so far? So, what is T mu nu? Let's consider the u mu in the rest frame of the fluid, where u mu is equal 1 and 0. This T mu nu is simply epsilon ppp. And we can boost that to write down a formula that could be valid in any frames. So T mu nu is equal to epsilon plus p u nu plus p g mu nu. This is the perfect fluid stress energy tensor that probably everybody has seen before. Any questions so far? This is general, just condition. You can derive, as you see, we have derived it. What do I mean by perfect fluid? So here, we have temperature and velocity dependence on space and time. So in principle, if I follow the philosophy of effective field theory, there will be corrections that are proportional to first order in derivatives. So derivative or first order in p and omega. So here I restrict myself at this moment to the leading order in the derivative expansion. Both terms contains no derivatives, so these are the zeroth order. If I insert that into the equation of motion, that would be the zeroth order equation of motion for a fluid. So starting from any initial condition, we can find the subsequent evolution of the system. Okay, so let me also write down here some facts about the relationship between pressure and energy. Pressure is a function of temperature. In a conformal system, for conformal theory, the pressure is restricted by scale invariance to be some constant time t to the fourth in 3 + 1 dimensions. And then the energy density is, and then dP is equal S dt, and the energy density is Ts minus P, and for conformal, if we have conformality, epsilon has to be equal 3p. Or we can write this as the condition that the trace of the stress tensor is equal 0. The equation of the usual way that hydrodynamics is presented in textbook is that we have the equation, we take some initial condition or some boundary conditions, and then solve the equation of motion. Here in this lecture, I will take a different perspective. Let's assume that we couple the system to external metric perturbations. So I will assume that my metric, namely not the perturbation of the metric, g mu nu minus eta mu nu, we have suffer some perturbations, and then I will look at the linear response, or if I want to go in higher order, just the response of the system on metric perturbation, and from that I'm going to derive the correlation functions. Okay. I know the equation of motion. I have to couple the system to the matrix, and then I'm going to find the correlation function of the stress energy tensor. Okay, so in curved space-time, what we do here is that we just replace that one by a covariant derivative. So before solving the equation, let me mention one particular and interesting properties of these equations. One can check that this equation has not only scale invariance, but it has the full wide invariance. That is, if you do a rescaling of the metric tensor, and at the same time rescale the temperature and the velocity by appropriate factor, you can easily check that this equation remains invariant. So the last line should be omega times u. U mu. Yeah. Sorry. U mu, so that u squared is still equal -1 if you combine these two. The fact that it is wide invariant is perhaps not accidental. The quantum field theory has the quantum field theory is wide invariant up to terms that has 4 derivatives. So if you write down T mu nu square, the T mu nu in the curved space, typically it is something of order the Riemann tensor square that contains 4 derivatives. In hydrodynamics, at this level, we are working at the leading order in hydrodynamics with no derivatives, so we will see the full wide invariance of at the level of the equation of motion. Okay. Now let us talk. Yeah, any questions so far?
To prove the value invariance, we need to use the conformal condition that P.
Yes. So that while invariance will be valid only if the equation of state of the fluid is conformal. Okay. Now let us discuss these terms, the corrections. So this correction might seem to be always suppressed, but they have an important effect, namely within ideal hydrodynamics, you can derive by taking u mu, you dot the equation of motion with another u, it equals 0. From that you can derive the equation of conservation of entropy. So entropy is conserved within ideal hydrodynamics. If you want to describe dissipative effect, the production of entropy, you need to go at least one order beyond the ideal hydrodynamic order. So these are the term proportional to first derivative that we are going to write down right now. So what are these terms? So let's call that tau mu nu. Let's call this tau mu nu. Okay. So before writing down the expression for tau mu nu, let us also notice that the form of tau mu nu is actually not completely fixed. We can always choose to make a shift in our definition, say, of the velocity. We can say that instead of using one definition of the velocity u mu, let me shift that by a small amount. Where small here I mean of order of one derivative. Okay. And that would, in order to keep T mu nu invariant, I have to change this tau mu nu, and that induces a change in tau mu nu that contains one derivative. Okay. So there is a redundancy in the in this way of writing T mu nu. The redundancy, there are 4 redundancies because there are 4 variables that we can shift by a small amount. So in order to fix this redundancy, we choose a gauge. In some sense, we have to choose a gauge, and the gauge that we usually choose is u mu tau mu nu is equal 0. So you can see here the number of equations that fix the gauge is equal to the number of the small shift in the in T and U that we can make. Okay. Physically, what this equation tells us is that in the rest frame, where U is equal 1, 0, there is only tau ij. There is no component of the non-ideal part of the stress energy tensor that has a 0 index. In other words, all the conserved densities, the T00 energy density and T0I are all given by ideal hydrodynamics. And only in the stress tensor there is a non-ideal part. Okay.
So the variation doesn't include kind of complement transport. I mean, we can request that the order 1 in the T is also conformal levels of traceless.
this this
That T mu.
this T mu nu has to be traceless.
I mean,
This,
that conditions, the relation of U mu and
so this is just, I'm just writing, say, if you have a stress tensor, you have to decide what it corresponds to in terms of temperature and velocity. If you have a fluid at rest in exact thermal equilibrium, you know exactly what is the temperature and what is the velocity of that fluid. But suppose you have a fluid whose temperature varies over space and the velocity also varies over space. If you pick a point, there is an inherent uncertainty in the measurement of the velocity and the measurement of the velocity. So that uncertainty reflected into this arbitrariness in shifting the u and the temperature by a small amount proportional to the first derivative. Okay. And that has nothing to do right now with the conformal invariance. It can be this redundancy occurs in any theory, okay? And we are trying to fix that using this condition.
so that gauge condition decide everything in the.
It has there are 4 equations, so it one should be able to fix everything from that. So basically, how we so the number of equation is equal to the number of redundancies. So completely fix the everything.
Just asking, if you do that kind of transformation, U mu goes to U mu plus delta U mu.
This is not a transformation. It is just arbitrariness in the change of variables. That from this change of variable allows us to shift some part of this ideal part of the stress tensor into this non-ideal part, and vice versa. So since I'm right now I'm going to write down the expression for this non-ideal part, I need to somehow fix the division between the ideal part of the stress energy tensor and the non-ideal part. Okay, so there is degrees of uncertainty. How do I shuffle the stress energy tensor between terms with zero derivative and terms with non-zero derivatives? And that is the arbitrariness that I want to fix.
You would get such an arbitrariness at every order in derivative expansion, right?
At
every order in derivative.
Once I fix this one, there is no other. There is there are 2 derivative terms.
Which means you could add u mu plus something even smaller.
Yes, but this equation is supposed to be valid to the same number to the same order as the order that I'm considering. So this condition in the hydrodynamic literature is called the choice of Landau-Lifshitz frame. It comes from the choice that Landau and Lifshitz made in their textbook. Okay, so now we have to write down this tau mu nu. Since it is perpendicular to u, it is useful to introduce a projection of projectors, the projector onto direction perpendicular to u. So I'm going to introduce this one. So this one has the properties that u dot p is equal 0. Okay. And from Lorentz invariance now, the only thing I can write is p mu alpha, p mu beta. Okay, so I projected so that tau mu nu is perpendicular to u. Okay, and then here I can write things like alpha u beta, beta u alpha. I have to make sure that the stress energy tensor is symmetric. And for the conformal, I will always consider conformal fluids. I have to make sure that it is traceless. and one can easily see that the way to make it traceless is to subtract the trace. And there is one numerical coefficient in front of this expression that is called the shear viscosity. Which equation? So there is no. I don't understand. No, this u is just the velocity of the fluid. It doesn't. We are right now in a. Say you can do that in Minkowski space. This u can change from place to place. So this in general. If the fluid moves as a whole. In one direction, then there is no dissipative part of the stress tensor. Okay. If now it moves with different velocity at different point, the u is no longer a killing vector, and you will have non-trivial contribution to the stress tensor. Why? I'm sorry. To P. So I want to make sure that this condition is satisfied. So to satisfy that, I have a single P mu nu will satisfy. So we can, in principle, write down another term that has a single P mu nu. Here, that will have a non-zero trace. And so this one is actually called the bulk viscosity. And in the conformal fluid, when T mu nu has to be traceless, zeta has to be equal to 0. But in general, there is a bulk viscosity. So physically, the shear and the bulk viscosity tell us how much entropy is produced when we have a flow of liquid that has a, in the case of the shear viscosity, we have a flow that's go this way when the fluid moves this direction, and the bulk viscosity is the dissipation of the system under isotropic squeezing and expansion, as it is apparent from this structure here.
Why is Lorentz invariant for finite temperature system?
It's a good question. The system, if you consider equilibrium state, the state of the system is not invariant under say boost, right? If you have a system at rest like this, you boost it, clearly it goes into another state. However, the physical law that governs the microscopic of the system is Lorentz invariance, and you have all the consequences of Lorentz invariance, like the fact that the energy density, the energy flux is equal to the momentum density. At the level of the formalism, the state, the equilibrium state, corresponding to u mu equal 1 and 0, is not invariant under a boost. If you boost that, you will get another state. But the equation of motion that governs the dynamic of the system has to be Lorentz invariance. You can think about that also this way. If you have a system like this, and then you suddenly somewhere a supernova explodes, and you have a gravitational wave propagating through it, And you have to know how the gravitation field coupled to the system. And the only way you can do that is that if you have a Lagrangian or the equation of motion that has Lorentz invariance, and then you can replace the derivative by covariant derivative. Okay. So which is what we are going to do now, or very soon. So let me that. Okay. So why? In the tau mu nu, the dependence on temperature is in here. So in principle, so this eta has to be a function of temperature, and this zeta has to be a function of temperature. Scale invariance would actually tell you how, if there is a scale invariance, then this eta has to be proportional to t cube. By counting the dimension. This one is dimension 4, this one dimension 0, dimension 1. So eta has to have dimension 3.
Derivative in temperature.
Oh, derivative with respect to temperature. Suppose you want to include derivative of temperature, then to this order you are restricted to one derivative. The mu t would be a higher order in derivative, so you don't consider that. Now you have to have another index, and the only thing that have a free index is u nu. And then if you do this, and then you will not satisfy this condition. So this condition get rid of the so-called heat current. If you have gradient of temperature, you have a flow of momentum.
Last question. E and B. Why don't we have energy and pressure? The thing that appears in
Which term you are talking about?
epsilon and P.
Epsilon.
Why is the viscosity different on pressure?
Let's recall, we have a system with which is in thermal equilibrium is characterized only by the temperatures. When the temperature is fixed, the pressure is determined. Say if you're talking about QCD, we would go to QCD lattice theories and ask what is the energy density and pressure at this temperature. So everything can be expressed in terms of the temperature.
So the time dependence of the eta and psi is only time dependence even in the case of non-conformal.
There is a time dependence, temperature dependent.
Temperature dependence.
Yes, there is.
In the non-conformal case.
In the conformal case, this one disappears, but this one has the temperature dependence that is governed by scale invariance.
What I'm saying, even non-conformal case.
In the non-conformal case,
depends only T still.
this has to be T only, because the only scalar characteristics of the system is temperature. Suppose you have a fluid that moves, you can always choose a coordinate system so that this particular piece of the fluid is at rest. And then you ask, what is the characteristics, what parameter characterizes the state of this fluid? Since everything is already thermalized, there is only one temperature. Everything else disappear due to the assumption of local thermal equilibrium.
The reason why the heat current term doesn't show up is because it breaks the gauging rate.
It's because we have chosen the definition of the velocity so that its flow with the same, so that this term disappears. In other words, we choose the velocity so that, in very rough sense, all the energy current is in these two terms.
Relativistic theory has infinite thermal conductivity because the energy current is the momentum density and it's also conserved. So that's a physical property that's unusual.
Right. I have trouble thinking about this a quantity that doesn't exist in this thermodynamic limit.
Yeah, there is no thermal conductivity.
There is no thermal conductivity at all. Yeah. It doesn't depend on whether the transport is ballistic or not. As you said, the same T0I is both energy current and momentum density. This is not usually.
I agree. I think that is ballistic.
Yeah. Momentum density. It is not usually encountered in condensed matter physics because the Lorentz invariance always broken there.
Well, once you break Lorentz invariance just by adding a non-zero charge density, that's enough
Then,
for finite thermal conductivity.
But there is an exchange you can do. I'm not going to talk about that, but you can exchange that thermal conductivity to a diffusion constant of the conserved charge. So there is one common kinetic coefficient that govern both quantities. Yeah. Okay. So what is our next? This on this board is the summary of everything written in one chapter of Landau and Lifshitz volume 6 that we are going to need, I hope, plus something more that we actually turn on external gravitational. We assume space-time doesn't have to be flat, and that is going to be useful for us because we want to compute using the hydrodynamic equations the correlation function of the stress energy tensor. So let us recall that in thermal field theory, one can define, as we talked about that last time, the full 2x2 matrix of the stress of the correlation function. The correlation function we are going to be interested in here is the correlation function between two components of the stress energy tensor, and they have 1, 1, 1, 2, 2, 1, 2, 2 components in the closed time path formulation. We also know that there is we can introduce the notion of retarded screen functions. Retarded screen function is G11 minus G12. So let's choose sigma equals 0, the choice of the contour. The retarded green functions, as we explained in the previous lecture, is the one that appears in the linear response formula. If we introduce into the system a small perturbations, in this case gravitational perturbation, by exploding a supernova somewhere or doing something else, then by measuring the expectation value of the stress energy tensor at point x, we can extract the retarded green functions as a function of x minus y. So the formulation of hydrodynamics that we have on this board is unusual because we are using equation of motion instead of Lagrangian, but that allows us to compute the 2-point retarded Green function at least. We don't know. I don't know how to compute arbitrarily the Green function of the product of n elements of the stress energy tensor, but for 2-point function there is a well-defined recipe. Okay, so the perturbation we are going to use, let's go into momentum space. So we are going to induce in the system a linear perturbations that is a plane wave, and actually I'm going to have a plane wave propagating along the third direction. So h mu nu is going to be equal to a plane wave times h mu nu, that now is not a function of t and x. Okay. So this is completely external field. It doesn't have to satisfy any Einstein equations. It is just a background we turn on. In principle, we have to take a linear combination of all these perturbations to have a perturbation that is localized in space and time, but I'm going to ignore this issue. Okay, so we have chosen Q to be 0, 0, Q. So we have broken the SO3 rotational symmetry. All the perturbation, on the other hand, can be classified with respect to the SO2 rotation in the x and y direction. So our wave is propagating in this direction, and the gravitons, the gravitational perturbation can be all classified in terms of the properties under SO2. For example, is the H12, for example, let's call that Z, because I'm using HY XY, or HXX minus HYY will be a spin 2 perturbation. It's a tensor with respect to that, two index tensor with respect to this SO2. And we have, for example, HTX, HZX, and HTY, HZY would be spin 1, because it has one index X, for example, that point along this SO2 directions. And there is another class of perturbations, HTT, for example, HZZ, HTZ, HXY, XX plus XYY. That is the spin 0 perturbation. And we expect that all these perturbations can be treated independently from each other because they are transformed in different representation of this SO2 transverse group.
Just so I'm clear, the y is actually the coordinate you're momentum in?
Yeah, so X, Y, and Z. So here I'm just considering most general perturbations of the metric, and then I break it down into different cases. And we will see that in different channels we will have correlation functions that exhibit different properties.
Isn't it true that in SO2 you do not have traceless two tensors, and we can only have vectors and scalars, right?
Okay, so here let me see. So if I have a tensor Aij, right? So I will not have this problem if there is one more dimension. But let's assume there is SO2. Then I can construct Aij minus delta Ij Aij, for example. If Aij is symmetric, that would still contain a trace part and a traceless part. Yes. So here I'm breaking this is the traceless part of this tensor.
They're all one-dimensional.
Sorry? They are all.
What I mean is, like you have one is the traceless condition. That's one constraint. And for a graviton, you also have the divergence-less condition, right?
Well, here my gravitons doesn't satisfy any condition because I just this is just a background that I can turn on arbitrarily. It doesn't have to solve the free Einstein equations. So this is so that's otherwise there will be no not that many components, independent components that one can turn on.
So if I were to consider this current coupled to the alternating solution?
So in the Lagrangian, imagine that we have a Lagrangian, and then we couple that Lagrangian to G mu nu. So if I expand that, I will have H0 plus H mu nu T mu nu plus etc. So that G mu nu is in my background field. H mu nu is the perturbation. So in principle, there is also H squared term here, etc. Okay. That is required by gauge invariant. Okay, so now we are going to derive the so-called Kubo's formula. So for that, let us turn on perturbations of this type. So H, let's assume H x y not equal 0, and H x y is equal to e to minus omega t. In principle, there could be IQ z here, but for simplicity, I will put q to be equal 0. So turn on, when q is equal 0, actually things become much simpler because everything now can be classified under the SO3 symmetry. And here I'm turning on tensor perturbations in SO3. So imagine I have this cup of fluid, and then I turn on some wave, some tensor wave that propagate. It doesn't have to be a wave right now. I'm doing just a constant in space, but time-dependent perturbation of the metric. So you can think about this way. This metric, if you draw a cup of fluid, right, and then you draw some. Let's see. This one is the XY direction. You imagine you draw some imaginary circle in this fluid, and then you do some perturbations. This perturbation is going to. You can think about this as a perturbation of the space-time. So this the circle will become an ellipse, and it oscillates in time. So you have an ellipse that oscillates in time. But on the other hand, you can also think about this problem as just a motion of the fluid. You have gravitational potential going through this, pull the fluid in different directions. So there is a motion, and this motion is sensitive to the shear viscosity, because this motion has a non-zero shear. So physically, what we are going to do is that we are going to see how the fluid responds to this motion. Okay, but here in this formalism, we see that we turn on a tensor perturbation that cannot couple at linear order to anything that is scalar and vector. So the temperature, if we have a fluid that has constant temperature, turn on some tensor perturbation, the temperature has to remain the same. So T equal T0, perhaps with some correction that has to be quadratic in power of the perturbation. It cannot be anything linear, right? From a tensor, we cannot, from a traceless tensor, we cannot make a scalar. Also, the velocity of the fluid, right? So if you think about the velocity as 1, and then plus O of V squared V. The velocity, if the fluid is at rest, it's likely when it moves under a small perturbation, it can move only slightly. So the velocity will be much smaller than 1. This correction will be a V squared. But this V is a vector under SO3, and it cannot couple to this tensor perturbation that we turn on. So this V also goes away. V is equal 0. So at first sight, the fluid cannot respond in any manner to the gravitational perturbation. Just it used to have constant temperature, 0 velocity, and now we see that it remains to have constant temperature and 0 velocity. We do not excite any mode. However, let's look more carefully at the stress tensor, stress energy tensor. So it's T mu nu. In particular, I'm going to look at the Txy component. Okay, so that one is, as we see from that, the ideal part. There is only P Gxy. Okay, so this one will be guaranteed to be non-zero. It's actually equal to minus P Hxy plus, now let's see, minus eta gradient x of v uy plus gradient y ux. Okay, so the thing is that here we have covariant derivatives, and covariant derivative is the usual derivative minus the Christoffel symbol, xy, and then there is a mu, u mu. So the metric may appear, if it appears, it will appear in this Christoffel symbol.
But you consider filter G alpha beta partial.
Sorry, if I'm rewriting this one, so it's xy, right? So the projector will. So there is this one.
You consider those terms.
I consider these two terms. This one is gxy times derivative of u. So let's see. This one will be gxy. So there is a term like this there, but d dot u will be we introduce this system would be a nonlinear term because it's proportional. We are working at the linear order in H. So this u, so first of all, this u is not the derivative will contain another power of the perturbation. So if you write down this term, g alpha beta d dot u, right? It is equal to gxy d mu, so 1 over g u mu. When you look at that, this one is one first order in H, right? And this one will be at least another order in H, if not more. So it will be a term that is proportional to H squared. To leading order, this is 0 because u is a constant and g is a constant. To leading order, the derivative of a constant will be 0. So this term will contribute, but to higher order in the perturbation. So have any more questions? So the to leading order, again, this one will be just the only contribution to leading order will be when this index is 0, because this where this u0 is 1, minus 1. And by computation, this is just proportional to the time derivative of hxy. So, with all that said, I think with the sign here that I'm not going to try to make it correct, I have eta times hxy dot. And this term, this might be minus. Yeah, but you could easily figure out the sign here. Okay, so what we see, we are not exciting any mode of this hydrodynamic mode of the system, but the system still responds in the local way to the external perturbation, local in space, in time, local in time. For example, the stress energy tensor, the expectation values be proportional to h and the first derivative of h. So here again, there might be the correction to this formula are proportional either to h square or to momentum square, to frequency square. Okay. That Now let's look at this formula. This formula tells us that from the expression that we have derived, we can read out the Fourier transform of the retarded Green's function of the stress energy tensor. For this component, the retarded Green function is equal to this real part, P, plus imaginary part minus I eta omega. I know this sign here is minus, so plus, so I think this one has to be minus as well. So let's see. So this one, the P here can be thought of as the contact term. If we Fourier transform, it's a constant in momentum space in omega. If we transform that, we will get something proportional to delta t. Actually, it's delta t delta x. It's a constant term. This one is a polynomial over omega, but it has the imaginary part. It cannot be a contact term. It cannot be changed by the redefinition of the correlation function. This one is a physical object. So we can write the following formula. Since this formula is correct at small omega, we can write it is the minus the limit omega goes to 0 of 1 over omega, the imaginary part of the retarded Green function xy as a function of omega. This formula is called the Kubo's formula. And it relates the kinetic coefficient, the shear viscosity, to a correlation function in quantum field theory. Any questions? So this formula actually will underlie all the calculation of the shear viscosity from the ADS-CFT correspondence that we are going to try to make. Okay, so here, as we said, there might be term of order omega square. Okay, and in general, actually, one thing I will use the occasion to mention here. Actually, the first correction will be omega to the power of 3/2. And this one has a very interesting history. It was first observed in computational simulation of a classical gas of like Miller bore, and they see this term. And then it was understood later as the result. Basically, one can think about that as the as doing effective field theory at one loop level, to some in a certain sense. Here we are doing everything in terms of the equation of motion, so it's not clear what does it mean to do a loop calculation. Actually, there is an equivalence of doing one loop calculations, and the one loop calculation, in a way that is similar to chiral perturbation theory, has the infrared singularity that tell you that is dominated by the hydrodynamic degrees of freedom. So you know that this correction is equal to omega to the power of 3/2, and you know exactly this coefficient in terms of the viscosity and the equation of state. Yes?
If you plot this function, which has, so it's omega equals 0, intercept is eta.
Mm-hmm.
And in a weakly coupled gauge theory where there's a transport peak, is this the function which has a peak whose width in omega is the mean free path, or the mean free time? Or is that a different one of the, is that a different spectral function?
This is the same. Yeah,
Yeah,
I
so
think this is
Yeah, so
to think about that, but I think this is
I've just lost
the same. Yeah.
There is a spectral function which
I think this is the one like that. It is 1 over this 1 over omega time imaginary part.
If I take an analogy with charge, this is like a current correlation function, but the thing that has the peak is the density correlation function. Maybe it's the momentum density that will have the peak that you're referring to.
No, I think the momentum density will have a peak that is a different. That is different. This one is the correlation function of something that does not have to have a pole in the hydrodynamic theory, but the width of this region. So this limit is approached when omega is less than the inverse mean free path. In a weakly coupled theory, this limit is approached at very small omega. So that's what Krishna was talking about.
Just so that this spectral function is a nice way of telling whether you do in fact have weakly coupled quasi-particles in the system. Because if you do, it means they have a long mean free path. They can transform momentum. You get a significant shear viscosity. So it means two things. It means eta goes up, shear viscosity goes up, and it also means there's this peak near omega equals 0, and the width of that peak tells you the mean free time. So if you see such a peak near omega equals 0, it's a sign of a weakly coupled theory with quasi-particles that have a well-defined mean free time.
So I'm going to draw what is this function looks like. So in a weakly coupled theory, you would have a peak, and then there's some behavior like this. And in a strongly coupled theory, you might have a featureless. So it is when lambda is much less than 0, much less than 1. Lambda is of order bigger of order 1.
The lambda bigger than 1, I would make the eta smaller. I mean, two things happen. One is
Yeah,
the peak
this
goes
is.
away and there's the intercept.
Yeah, the intercept would be more like that. Yeah. Now there is an interesting question of whether there is the area of this region, area below this curve, satisfied a certain sum rule, and the answer is that you have to subtract the vacuum part, and then there will be a sum rule. There is a sum rule that's not completely worked out, but there seems to be a sum rule. Okay, so let me now briefly mention to you what would happen if you do the same calculations, but perturbing the metric not in the spin 2 sector, but in spin 1 or spin 0 sector.
What is the coupling exactly entering into?
Okay, so right now all this calculation is done within hydrodynamic theory. So we don't know anything about the coupling. So here I'm just trying to tell you, but not in detail, the form of this green function. It always approaches a constant, and this constant is the shear viscosity. But the the omega dependence of these functions, as Krishna said, have difference in weak and strong coupling. At weak coupling, the regime of validities of the hydrodynamic theory is very narrow because the mean free path is large, and so we have to go to very small omega in order to reach this limiting value of the spectral function.
Is that minimum when omega is towards the temperature?
So this one is when. So the scale of this region is 1 divided by the mean free path. So the mean free path in, say, a gauge theory would be g to the 4t log of 1 over g, or something like that. In fact, there's a coupling in here, and in fact, in order to figure it out, it's rather it's not that difficult to figure it out. You have to just look at the kinetic picture of gluon propagating in the medium, and look at the cross section of this gluon scattered with other gluons, and see what is the mean free path. And that mean free path will be determining the width of this region.
So the problem is that as the
take the things thermalizes over a length scale that is large compared to the temperature. So if you do the same experiment with this gravitational perturbations, you reach the hydrodynamic limit only at very low frequencies. Only at very low frequencies, things manage to equilibrate between the two subsequent oscillations. So that basically is the. So very briefly, what would happen if one, for example, turn on perturbations in the, for example, for these two components, for example, suppose I'm perturbing the system in this sector, and then we can, from symmetry, we can say right away that there will be no temperature perturbations at all, because it's spin 1, but the velocity, there will be a small velocity. U will be equal to 1, and then a small Vx, and then 0, Vx, much less than 1, okay, of order h, let's call that. Okay. And again, you can write down the equation of motion of a fluid in a curved background. I'm not going to do this exercise. You will have one equation that comes from this equal to some force. The force basically comes from the gravitational perturbation. Okay. And this one contains, so we have to use the that is proportional to h. That can be worked out. Okay. And now it's we can also write down what as the T0x and Zx to leading order in the perturbations. So this one is epsilon plus p time Vx, and this one has the only components that is non-zero is actually this shear viscosity minus eta, and then dz Vx. So when you work out every possible term, you'll find that it is equal some force. So something. And we can write this as the in the left-hand side, you can see just the usual heat kernel, where this is the, if this was 0, it would be a diffusion equation for x. And that means that once we solve these equations, what we will find is that there is a pole in all correlation functions, and the pole is located at the position determined by the quadratic by the operator multiplying Vx. So we have poles at omega equal minus I eta divided by epsilon plus p q square. If you compute the correlation function, they will have single poles located at this position. Because when you solve these equations, right, there's Vx equal to force, some force that I don't write down, divided by I omega plus eta over epsilon plus p q square. Okay, and that pole will be inherited by all the correlation functions. And you can work out all the correlation function exactly. And here in the spin zero channel, I will just quote the result. What one will find is that all the correlation function will have a pole at omega equal some VQ minus 2/3 eta divided by epsilon plus P Q square with the factor of I. So this pole here actually has a rather trivial physical meaning. It is a sound wave that propagates with velocity v and has an attenuation proportional to q square. This is the imaginary part. Basically, we are here perturbing, say, if you turn on HTT, we're perturbing the energy density. We couple a source coupled to the energy density of the system. And if we change the energy density, we will set up a ripple in the plasma, and the ripple propagate at some velocity v that in the conformal case, v is equal to 1 over root 3. And the attenuation is, again, proportional to the viscosity. And this will, you can do that by following the algebra of the conservation law. So this one is closest to quasi-particle that we have. Here the real part is much bigger than the imaginary part. But let me emphasize that that is not a correct thing to say that the sound wave of a plasma at finite temperature is a quasi-particle, because the frequency of this excitation is much less than the temperature. So the occupation number of this particle is much bigger than 1. So we cannot talk about the quantum fluctuation. This mode is not a quantum fluctuation. It is a classical fluctuation of the thermal medium. Krishna?
One thing to point out is that epsilon plus P is proportional to S, the entropy density.
Mm-hmm.
So this shows you, eta always comes in like eta over S. Which is not always from any other formulating on the board, but it's clear in the sum.
It is some kind of coincidence, I think. You can here in this lecture we are concentrating on in the case of a plasma with no chemical potential. If you do the same calculation but with chemical potential, you will see, for example, that this formula and this formula doesn't change. On the other hand, there epsilon and P sum up to Ts plus mu n. So it's only when mu equals 0 that eta over S appear in the formula. As we will, so running ahead, ADS-CFT, the ADS-CFT correspondence tell us that in models with Einstein gravity dual, the ratio of eta over S is constant, but not 1 over 4 pi. But it is constant even when chemical potential is present. So, okay, yeah.
I just wanted to see if I understood the spin 1 case. The idea was like sending in a gravity wave with
gravity wave that would particularly polarize along this direction. So we would push the fluid to move along this direction. But on the other hand, this gravitational wave propagate in the perpendicular direction. So we'll have a fluid that moves like this. You would have a fluid that would try to move with velocity changing in space like this. So it will move in layers, and different layers will exert friction on other layers. So that's why this is overdamped mode. This mode is overdamped. This mode is a mode where the fluid moves like a longitudinal sound. So it's a compressible fluctuation of the system. And the damping is much less than the real part. And it's parametrically, the ratio of imaginary part over real part goes to 0. So the low frequency sound always travel longer than the high frequency sound. You can actually see that in when you hear music from afar. That's what happens. Yes.
So for the pole at the spin line case, the omega is always imaginary, right?
Yeah.
This means some decay. Or
It is an overdamped mode. Yeah, this when you set up using this perturbation, something like this, it will decay exponentially in time. There's no oscillation at all. Yeah. If you have a solid, for example, you will set up an oscillation, but with a liquid, there will be no oscillation. Yes.
Wait, where's that Kubo formula for other formulas?
If one has, for example, in the system with U1 conserved charge, you can write down the Kubo's formula for, say, the conductivity. So if you turn on a background gauge field and measure the current, the conductivity will be also limit omega goes to 0 of 1 over omega correlator of two components of the arbitrarily chosen component of the current. So you can also write down Kubo's formula for the current. So in a similar way, turn on an electric field and see how the system responds. Any other questions? Okay, so next time we will talk about ADS-CFT finite temperature calculations.